Hello guys, I'm sure you're doing awesome. Let's talk today detail about the NoSQL and its internal. So today's our discussion will be mostly regarding various kind of optimizations that has been done in the NoSQL databases to make it scale seamlessly, and also we will see how exactly with a very optimized read and write path NoSQL works optimally. So first of all, like before jumping into the discussion, let's talk about one of the misconception that often many engineers have. So NoSQL is there is no particular kind of a database is being known as a NoSQL. Rather, NoSQL is kind of a family of the databases. So if I if I have to segregate it into the different families, you see the MongoDB. MongoDB is kind of a document DB. You see Apache Cassandra. Apache Cassandra is a columnar storage. When you talk about Neo4j, it's a graph storage, and things like DynamoDB and the Redis or the RocksDB, they are the key value store. So let's talk about each of this thing in a very small detail. We won't be able to go into the internals of all of them, and what we will do is we will try to go into the internals of the key value pairs. Okay, so what are the four major types of NoSQL that we have just discussed? So the first one is the document DB. The document DB is Mongo is the most popular example of that. Then there comes the key value pairs. So in key value pairs, a lot of things will come, like Dynamo of AWS Dynamo. This is anyone who is using cloud managed platform, it is probably the first choice. Then there is Redis. Then there are things like RocksDB, and after that there are things like the graph. For the graph database, Neo4j is one of the very popular one. Again, this is something like we will just on the surface level we will touch upon them, and we will try to see how much we will try to see the key value pairs in depth. Okay, and also like one of the very popular thing for the data storage behind the scene of the log aggregation platform is the columnar storage. So columnar storage is like Cassandra, Redshift, etc. Okay, so these are the four major type of NoSQL. Now let's take some use cases and try to understand which one fits in which scenario. So in the use case one, let's talk about like a e-commerce platform. Okay, in our e-commerce platform there could be multitude of data, but let's concentrate upon the product information, including the name, price, category, tags, something like this. Okay, a complex data structure as this. Okay, so this is basically product catalog information. Okay, and it has even the nested reviews. It has all the variants that are being available for the users. So in this case, what will be the perfect thing is the document DB shines on top of everything. Why? So in document DB, we have a very rich querying facility. Suppose I want to search by some kind of a ratings. Like I want the ratings to be greater than 4.5. Then only show me the product. Okay, so writing this kind of query is very easy in a document DB. Plus it gives you, of course, being a NoSQL, it gives you a flexible schema. So NoSQL means like there are no relations between any two tables. Rather, if you want to establish any relation, you establish it by your own code or your own implementations. Okay, so here why key value pairs won't be suffice here, because it gives you very limited querying capabilities, like limited query. Why? Because at first I need to go through all the keys, then only I will be able to do a where clause on top of them. So similarly, it will be like a overkill for the graph, and for columnar storage, like it is very problematic to handle this kind of complex semi-structure data. Okay, it is not optimized for this kind of complex queries over this unstructured data, and that's a completely separate use case. So just try to understand why the document DB shines on top of everything in type of this kind of cases where we have a lot of nested data, and we might have to go inside that data on a very to query something. Okay, so now let's talk about another use case. So the use case something like the real time session tracking. Okay, so real-time session tracking, what exactly is that? A website needs to track the user sessions in real time, like how many users are coming in and how many users OAuth token or the authentication tokens are getting expired in a given timeline, or whether it is at all getting expired or not, like page views, all kind of data. So suppose I have a data structure like session ID, user ID, timestamp of page views, and session duration, things like this. Okay, so if I have a data structure like this, let me just paste it for your convenience. If I have a data structure like this, then key value pairs are the best case for us, because our key can be session ID, and it is a very high throughput system. Like key value pair, when we go into the further internals of it, we will see that how SSTables or Bloom filter, those kind of things will come together and help this data to be very get fetched in a very fast manner. Okay, so now this is like high throughput. Once again, let me, I think I lost the cursor. Okay, yeah, key value pairs, it is very high throughput one, and also it gives you like near in memory performance. So how it gives near in memory performance, this is again goes into the internals. So this internals we will definitely cover, but not all the other internals we will be able to cover for the other kind of databases. So let's save your brain to some good brainstorming that we will do over this. So then come like the use case 3. Suppose I want to find out some information regarding my social media friends network. Okay, what kind of query I want to do? So I want to analyze like the friend of a friend relationships, shape, and suggest user. Now, or something related to, there are various nodes, something related to the shortest path of them. Various nodes, or you can see places. Okay, so this kind of things, the best fit is the graph databases. So what graph databases does is, like, it gives you some kind of a relationship modelings. So the relationship among the users, like who is following each other, or there are efficient path queries, like the follower kind of a thing, follower sort of a thing, or efficient shortest path, like various path optimized query capability is being given by the graph database. So in this case, the graph database definitely shines on top of it, and writing this kind of graph queries on key value database or in the document DB is very memory intensive and very difficult as well if you have to cater so many requirements around it. And then the use case 4 is fine, like suppose you want to do some kind of a analytics on historical data. So in this case of data, the main point that we need to cover is the aggregation. So if those datas do aggregate well, like on month basis or customer basis, or grouped by on a like quarterly basis or region basis, those kind of aggregation on various parameters, in this case columnar data storage is the best thing because it is optimized for analytical queries. So why and how the columnar database is optimized for that? Again, those internals probably in a later point of time in some other video I will try to cover, but for the time being let's just think in this way that columnar DB, this is basically can handle petabytes of scale and optimized for analytical query, primarily because like instead of row you store the data as columns. Okay, so when we are thinking around the columns, like this what I'm pasting is, this is a row, but the way it does is all the transaction ID will be grouped together already. So if you have to do some kind of a aggregation on top of user ID or in top of transaction ID, it is very much analytically optimized on that. Okay, so now our key value pairs uh, or the document DB, it's not at all optimized for this. Internally they are being done for, like they are being optimized for different kind of data retrieval and the very high throughput systems. So as discussed earlier, like as per today's scope, we will discuss around key value pairs. Okay, so we are going to discuss around the key value pair. So this is going to be our primary goal as of today. Now when we are talking about the key value pairs, you understand there are two very basic operations are there. Like there is a put, that is a key and a value, and then there is a get, which will get the key. Okay, so these are the very two vanilla operations that we can do on top of a key value pair database. No aggregation, nothings, only we get something and we put something. Okay, but the amazing part is the way this supports, the way this can be extended in various use cases and in very high petabyte scale, or rather I can say like terabyte scale. Okay, so as you can understand, like this put or get value, if I am just developing it under a single server, it is pretty easy. Like I do not even have to think about anything. Suppose this is kind of a database that I'm having, and in this database I will just keep on putting my key and values and keep on getting my key. Okay, and this will basically return me the value. This will basically return me the v of it. Okay, so we can just, how we can implement it, we can just create a basic hash table data structure and keep on dumping it into some file. Then with a good index read, we can keep on reading from that file. So it is again, like if I just have to write a very basic implementation, okay, this is something we can think of. So you can see, like I have created a memory cache, and in this memory cache I will just keep on writing it, and while getting it, what I can do is I can just keep on getting it. I can just keep on passing the key and I will get that particular object value. Now there are few other things as well here. Let's take a scenario, okay, and then try to understand it for a more what will happen in the large scale system. Okay, so suppose you building a user session management system, like we are building user session management system. Okay, so this is for a large scale web application like a e-commerce platform, and we need to store and retrieve user session data very efficiently. So this is the example session data that I have right now. Okay, this is the example session data that I'm having, and each user session is basically like on top of it there will be another parameter of session ID. So this is the basic data, and on top of it we are going to have the session ID. Okay, we're going to have the session ID on top of it. Okay, now each user session is represented by a session ID, and the value includes the information like a user ID, login, and whatnot. And this session records are, if you see, these records are actually pretty small. They will be something around 1 KB. Okay, but if you expect it to manage like millions of session daily, the system must support very fast reads and very fast writes, right? So like if in a sub-millisecond latency, every time I'm going to pass the session ID. Suppose session ID can be some kind of a like a hash based key. It can be 67E2 E1 2, in this kind of way we can have our session ID. So over this, the main requirement that comes in the scale, we need very fast write, because user keep on creating their sessions, and very fast reads. Suppose user keep on like logging into their sessions again and again. So in this case, like very fast write and the very fast reads is something that we is one of the necessary component of this system. Now in practice, this is the kind of a code we can write. So this memory cache is something that is holding some kind of a uh, in some way our key value pairs, and this access count is basically making sure that if the high frequency keys like which are being accessed very frequently, we should be getting them in a very less time. So we are putting it in a different way. Okay, now the moment we think about scale, one thing is clear, that we won't be able to accommodate all the keys in a single system. Like for the session ID, the user ID and the cart, suppose across the globe, Amazon is being scaled. So all of this information definitely cannot be done in a single server. So we have to go in a distributed server mode. And the moment we split our data into different servers, what would start happening? So the first thing we need to figure out in which server which data is there. So now we are going into our serious discussion where we will try to see how the systems, or how the systems would figure out in a distributed database key value pair DB, where exactly which data is being stored. Okay, so now our problem statements are getting a little bit more complicated. So before delving into this discussion, I hope like there are some basic concepts like cap theorem or like the hashing. Probably it is already clear to you. If not, you can take a pause and just look into that. uh, I am not taking in a scope to discuss the cap theorem or the hashing, consistent hashing particularly in detail in this video, because there are way too many good videos are already available in YouTube. for this, so you can spend a little bit of time on that and can understand this. So let's delve into the actual nuances of our implementation. So what we are going to start is, we will first step is, we will split our data, into different server or nodes. So now the question is, how do we decide in which node our data to be inserted, or which data should take in which node? So let's take this example. We are going to take, suppose, 3 key value pairs. Let me just walk you through this. Thing a little bit. So we are having 3 data over here, and our primary key is basically our user IDs. So based on the user ID, putting it as a key, these values are being inserted, or these values are being put into, suppose, a single server right now. Now we understood that this single server won't be enough for our need. So what will be our first step of division is, as a step 1, we are going to hash our keys. Okay, so how we are going to hash our key is, the key we are going to pass through some kind of a hash function. It can be like hash functions like MD5, SHA, or murmur hash. Many things are there. So just write MD5 or something like that. Our data will go through our, for example, this user 1001. This will go through our MD5 hash, and the data what we are going to have is, we are going to have something like a number. The number can be 987 something. I'm not just going into the detail of this hashing algorithm, but just per se think that there is a certain number we are getting on these hash values, and each hash based range we are going to assign to a physical node. So what exactly will happen is, like here, user 1001 will be having this value, 1002 is going to have another value like 1 2 3 4 5 6 7 8. User 1003 might have some value like 4 5 6 7 8 9 1 3. Okay, and then each hash based range, I mean, the rule will be set by us. The rule we will set that each hash based range that we are going to have, like 0 to 1 66666 some value, it will go to our node 1, will go to our node server 1, and there will be 1 66666 7 2, suppose 333333 2. This will go to node 2. So in this way, what we are going to do is, this different data, like all this all these values that we see, all the keys, they are going to get into different nodes. So ideally what will happen is, this user 1 that you see, this probably will go into, by this rule, node 1, because of the, based on the hash based range, this will go to node 2, again based on hash based range. Okay, and this will go to node 3. Now in this way, what we are going to have is, we are going to divide our data into different nodes. So just try to formalize it. I'm just trying to formalize it with a diagram now. Suppose there is a certain key, there is a key of a user 1003, and there is also a key for the user 1001. Okay, user 1001. There are 2 users are there, and this is our key. So both of these things will be passing through some kind of a hash based function. So we are going to have a layer of hashing here, and this will go through this layer of this hashing. both of them will go through this layer of hashing. And after this hashing, it will be decided that which node it will be going. So based on this hash functions decisions, so there will be, so this is basically our decision logic. This is basically our decision logic, and based on this, it will get distributed to different node. So suppose it can be in like node M, and this data of like 1003 will go to node M, and 1001 it might go to node N. Okay, so things will be like this, and what we are going to have is, this is going to be my primary nodes, and we are going to have, based on these partitions, we are going to have our replicas. So what we will do is, like, we will have a replica in multiple nodes. Suppose it can be, we can call it like node M1 or M2. Multiple nodes can be there, so it will be based on the replication factor. So I will just write it here as well. Can be node N1, N2, like this. Okay, N1, N2, in this way we should replicate it across. Okay, now let's this is a very simple concept that we discussed, that there will be a hashing engine. This hashing engine will keep on distributing the data. Now, why we need this hashing engine instead of like some range-based partition? For example, we can always think that we will just take the user in a different way. Like, why we are not doing it that user 1001 to user 1003 to node 1. This is because we might run into some kind of a hot data partition or the data sharding problem, because there can be in a certain region, there can be a lot of user with a certain user ID, which might lead to some kind of a data galore in a given node. So to avoid that, it is always advisable to maintain a hashing function and then use something called like what we have used here is hashing plus range-based partitioning. Okay, hashing plus range-based partitioning is the technique that we have used over here. So, and of course, there are multiple other things like consistent hashings and many things you might look into this. But for this use cases, like in DynamoDBs, this is enough, whatever we are having right now. Now, let's talk about one thing, how this system are being actually synced. I mean, how behind the scene this syncing happens. So, for example, like when do we consider that with a replica of mine that a data copy is actually successful in the replica and a transaction can be marked as a complete. So why replication guarantee is like super important? Super important for some systems. Suppose you are having a banking applications. Okay, so like your data you are reading from multiple servers. You are having two different replica of where your actual uh, balance is being maintained. Okay, so users balance is being maintained in primary and replica. Now suppose you are reading from replica and you are writing into primary. So if like in some way, if in some way our replication fails, the value or the account balance that I will read, user is errorless. Reading is error. And this is in a system like social media, it's a fatal. And when social media is like, when the replication is not very much required. So just for any kind of a social media app, Like replication might not be critical here. So just if you are thinking of social media app or number of like counts or the comment sections, do we really care that in a certain second I need to know that who all have liked a certain post, or if there are some delay between sync of likes or comment getting populated. Do we really care about that? Probably no. So replication might not be very critical in the system like social media. So what kind of replication guarantee that we are going to enforce in our system? That will be completely use case basis. There is no hard and fast rule that I am going to make my system like hard replication as a guarantee, or like replication I don't really care about. So let's try to see one of the like this data flow into a action in a more formalized way. So suppose again there is a user. So this user is trying to add something in his in his cart. Okay, so we were sticking to social media, so let's stick to that. So what will happen is it will at first go into our primary node. So here our primary node is there, and in our primary node some kind of a like a banking transaction, suppose. Okay, some kind of a banking transaction, and some 100 rupee got minus. Okay, 100 rupee deducted, 100 rupee deduction happens. Now what our primary node will do is this primary node will try to um, forward this request. Like once this is successful, so at first it will execute the transaction in this particular DB node, and when this is successful, when this part is actually successful, on success, what it will do is it will create a replica request. So it will basically write request to the replica node it is going to forward. So in this replica node we are going to have a syncing mechanism or a write mechanism in place. Okay, so the sync or the write will go into our replica node. Now once we get, so this acknowledgement we already get, right? So now once we get a acknowledgement from this level, okay, and plus this level, so all two things, when these two things come together, so basically this acknowledgement and the acknowledgement from this primary node, then only I will mark this thing as a transaction complete. So here in this stage only I will mark it as a TX complete. Else if we don't get this acknowledgement, in case we get a denial, what we are going to do is we are going to do a reversal of this transaction. We are not going to execute the transactions. So if we get a, for example, instead of acknowledgement, if we get a failure, what we are going to do is we are going to have a, at this level we are going to have a revert. Okay, we're going to have a revert in our primary node. So this is again for a banking system. And what happens during the social media system is, suppose you are having your primary node and your replica node, you just, the moment you get the sorry, let me write it here. Okay, yeah, so the moment primary node gets something, the moment primary node gets a request, and on success it will tell that okay, I'm ready to serve your data, and it just sends a like a sync request. So it doesn't really care when the sync will happen. So sync might happen in like in a 5-second delay, so it is completely fine for the system. And if there is a failure, it will keep on retrying. So sync with retry mechanism, because already I'm having a certain primary node which got which there is a success. So this is suppose for the Facebook comment. Okay, now we touched upon two very important concepts on consistency basis. So one is like this is being known as like very strong consistent system. So we need strong consistency at any cost, like for our banking app, and this is known as eventual consistency system. Okay, eventual consistency, this is maybe social media comment section, comment or like sections. Okay, and there are some other kind of consistency as well, but for the sake of our time we are not uh, going into the detail of it. But what you can do is, what are the different consistencies uh, between the system in a cap theorem. If you just search about that, you will get all the ideas, and they are very easy to follow and very intuitive. So now that we have our idea, like how this strong consistency and the weak and the eventual consistency happens, there is one more important concept I want to introduce over here is that is being known as quorum. So you might be having a question like, when does, so it brings up to a very good question, like when does a distributed system mark a write as success? Okay, so here the concept of quorum will come. So what exactly is the concept of quorum? So now suppose I am having a client. Client can be like a app or website or anything, just a user facing device or user, you can say over here. Okay, so what my client is going to do is, instead of directly passing the data to my primary servers or my replica servers, what it is going to do is, it is going to pass its data onto some kind of a coordinator. Okay, so there will be something, some kind of a coordinator. Okay, so what this coordinator will do is, coordinator will keep track in how many servers or in how many instances my write is getting successful. So suppose like that kind of a thing is happening, like the deduct 100 rupees, 100 INR. So what it will do is, it is having all kind of replica nodes. Okay, so instead of primary, just uh, instead of primary or replica, just name them as nodes. Okay, node 1, there are node 1, node 2 and node 3. Okay, so now when this write request comes, it this coordinator will keep on track of the acknowledgement. So suppose I am just sending this request to this as my first step. So what will happen is, this acknowledgement will come and it will, this is my request and this is my acknowledgement. Okay, this is my first step. So it will count that, okay, ACK equal to 1. It will count that, okay, ACK is 1, and then again what the coordinator will do is, in parallel only, it will send a request to node 1 as well. So again one request will go here, and the stuff that will happen from here is, from this we are going to get another acknowledgement. Okay, we are going to get another acknowledgement. So now what is happening is, the acknowledgement equal to 2. Now quorum exactly defines this number of acknowledgements. Now suppose I am sending this request to my node 3, but for some reason I am not getting any acknowledgement. This is a failure. Okay, suppose I get a failure, then what will happen is the acknowledgement will remain in 2. Sorry, the acknowledgement, the acknowledgement will remain as 2, but still I am going to mark my transaction as success and initiate a sync or retry, basically sync or retry for node 3. Exactly, this concept is known as the concept of quorum. So quorum means if my quorum I am putting it as 2, that means out of all my node, if there are 2 acknowledgement I am getting while writing, then I am good. I can mark that there is my primary node and there is my replica node. Among them, I am I'm having the data perfectly synced, and maybe there are other nodes which are not synced, but it's okay for me. I will initiate a retry mechanism on that. So this is what a quorum stands for, and the similar things happens for the read as well. So suppose I am starting reading my account balance, like this is basically a write flow. So similar thing happen for the read flow as well. So I'm just going to copy paste to optimize my effort a little bit. So suppose instead of deduct, read, okay, sorry, read account balance. So this is instead of read, this is a write flow. Sorry, this is a read flow. Okay. So now if same thing happens and I get 2 acknowledgement, in that case I am going to mark my transaction as success, and instead of initiating I will just return the data. So I know that 2 of my node is returning me the same amount, so my quorum is 2, uh, and my read flow I will mark it as a success. So what if there is only one single, like if my acknowledgement count is 1, for example this acknowledgement is kind of a, sorry, this is instead of a acknowledgement, this is a failure. I will just give the message to the user as unable to fetch your data right now, because there can be a wrong data I might be supplying to the user, because some node and the other syncing might be going on and I'm not getting the data in a correct manner. So that is why the concept of quorum will come in play. And in DynamoDB and in similar kind of distributed database, this quorum is the rule, and this quorum along with the replication factor is the rule which defines like when exactly I am going to mark my read or write as successful. Mark a write or read as success. Okay, so this is the concept of quorum, which is again comes with replication factor. So if I have to answer this question, so with quorum plus replication factor. So replication factor is basically my aim to replicate my data into 3 nodes. But if my quorum says like even replication of 2 is okay for me, then I'm going to mark it as a success. Okay. So that is why the read and the write quorum, all these things will come into play here. Now let's level up our problem, or let's level up like the kind of issue that we might get into a real world, um, the distributed or in the replicated system. Suppose I am like in Amazon, I'm doing some kind of a database design for big billion day sale. So big billion day sale, definitely like whenever this kind of event happens, Amazon actually scales their databases in a different way. Like for example, if you see Hotstar, they scale their databases in a different way for the semi-final or the final or any other kind of a special games. It doesn't work in a similar way to our normal scenario. So what might happen in my big billion day sale is, suppose in a city like Mumbai and its peripherals, previously Amazon is having a single servers. Okay, So initially, so now initially what will happen what has been happening is, in a single server my data is being located there, but I understood that a single server might with even replication might not be able to handle all the requests that I will be getting, all the write requests that I will be getting in a big billion day. So now in a high traffic scenario is that, like in previously what we understood is our data is partitioned. So our data is partitioned and put into some X replica, right? Now we were simping, we were syncing among them. Now the problem statement comes is, we are having two primary database instead of having a single primary database. We will be writing at the same time we are going to provision two database as primary one. Okay, so this database that you see, my so users request might come into this database, and the user request might come into that database as well. So suppose I have a user over here, so I have user A. So this users A request might go into this server of, suppose name it as Mumbai A and name it as Mumbai B. It can go to Mumbai A or it can go to Mumbai B. Okay, any of these things. So what is the problem that I might run into here? Let's discuss this now. So this user A is maintaining a cart. Okay, so a shopping cart. So and he's because it is a big billion day, so one time he is going into a mobile, and also sometime he is using his laptop, and for some reason this laptop and this mobile, they are into different, they are touching upon different spoons. So initially he decided that there will be 1 unit of spoons he might require, but then after 10 minutes just before ordering, he thought that, okay, no, I need unit, I need 2 units. Okay, so what exactly is happening is, from 1 this unit is becoming 2, and he is going to uh, make this request to this from his mobile. Okay, and then after using the mobile, he kept his mobile on charging, and he came back and he decided, "Oh, no, I need spoons of unit 2 just in a whisker of second before they even get replicated." So of course, like, you got the idea that we will always keep these two things in sync. We will always try to sync, but there is a syncing delay. In between the delay, in between delay, what he will do is, he will mark this spoon as unit 2 into the Mumbai B. Okay, so now what is happening is, like, Mumbai A is having the card value of spoons 2, and Mumbai B having the card value of spoons of, sorry, it will be 2, I have been spoons 3. Now when they were trying to sync, this guy will say ki, hey, I see this value of 2, and Mumbai B will say ki, I see this value of 3. So which is the correct value, which should be my, the exact value that I should be putting? And the answer is, this conflict that we see, the answering the conflict has manifold solution. There is no one fits all solution to this. So this is completely based on your use case. So what we can do is, one of the very popular methodology is last write wins. I will just write the whole thing, last write win, or LWW. Okay, so in LWW what happens is, we are going to see that, okay, this is the, so we are going to have a timestamp associated as well here. So suppose this has a timestamp of 1001 and this has a timestamp of 1003. So I decided that because this is my last one, so I will sync these values across it. So Mumbai B will also have 3 in his card value, and Mumbai A will also have 3 in his card value. Another thing is that, like, we do some kind of a merge with the numbers. So what we are going to do is we are going to do 2 plus 3 equal to 5. Again, it is completely based on case by case. So we write our own conflict resolutions in this way, that we manage this. So let's formalize it again. Okay, before going to the next step, there is one more thing we can do is, like, we can delegate it to client, delegate it to user or the client. That is, tell that I see a conflicting value, you please fix it. If you see a conflict, you tell me which is the correct value. So there can be multifold of solutions, and like there is no hard and fast rule for this, but just to formalize it, like suppose I am having this Mumbai 1, and also I'm having Mumbai 2. So when this two syncing will happen, when this two sync will happen, in between, I will just move it a little bit, these things. So in between, a conflict resolution will run, or conflict resolver, that will be the correct name. Conflict resolver would run, and what this conflict resolver will do is either it will do LWW, or last write wins, or merge, or send notification to client. This kind of conflict resolution strategy it might deploy and try to solve our use case. So as we promised at the very start of the video, that we will go into the internals of the write and read mechanism. This is the final part that we are coming into. So how the read write happens, I wanted to give you a wholesome idea at first and then go into the internals, so that you appreciate the whole system, how everything comes in together and powers up like a marvel of engineering, which powers like super useful database scenarios in our real world. So let's try to understand what exactly is the right path. So I will just try to write it through a diagram. It will be clear to you. So when the client request first comes, okay, when the client request first comes, it generally goes to our server. Okay, it generally goes to the DB server. So let's forget all about the coordinator or the conflict resolver, whatever you got. So this is the DB server that I am talking about. Okay. So now what happens inside the DB server? That is what we are going to explore right now. Okay. So this DB server, what it is going to do is, it is going to then write it in a something called a commit log. Okay. So this commit log is also known as like the append only log, or AOL also we call it, AOL log writing that happens. And once the commit log acknowledges, then what it does is it add it to a, I will write it in this way. Yeah. Once it acknowledges, what it will do is, after this commit log, it will go to the mem table, and we will come into all those things into detail, what exactly a mem table is, and there are a few other details like bloom filter, how they come in play. There will be mem table, and then what mem table does is, mem table will occasionally flush the data to the SS table. So lot of jargons here, we will just go into the detail one by one. Okay. Okay, so now we got to understand that inside a DB server, there is a good amount of process goes on, but let's try to understand what goes in detail. So a client sends a write request to the server. A commit log, it first persists the commit log onto a disk for durability. Okay, so this happens in our disk drive. Okay, so when we are talking about memtable happens in our RAM. Okay, it is a in-memory RAM or in-memory cache. And when a memory cache reaches a threshold, suppose memory cache have something like a 1 GB or some threshold we have defined, then it will start threshold of 1 GB. Then what it will do is it will keep on flushing the data to our SS table. So SS table is again disk driven. So this is the approach where you see there are two persistent log is involved here, that is the commit log and the SS table or the sorted string table. Okay, so why this approach is important is writing the commit log ensures that even if a system crashes, suppose this database server crashes in some way, and I just want to recover the whole thing, then I can replay the commit log. It is being also known as event sourcing. I can replay the commit log and this write can be recovered. Then there are things like performance, and for the performance what we do is we serve our frequently accessed data into the mem table. So I will just go into the top. So here you see, while we were doing this implementation, we were maintaining a memory cache. So in this memory cache, what we have been doing is, if it is a frequently accessed key, instead of going to disk, we are going to return our data from the SS table. So what happens is when a read request comes, we can always, like, we will go into the read request in detail, we can always go into the mem table at first, then we can go to the SS table. Okay, so write request is again, like as we were covering, write request were coming into the commit log file, and it is a simple append only log file in the disk where writes are recorded sequentially so that we can replay it at any point of time. Each write is appended at the end of the file as soon as it arrives. Okay, now this commit log, after this commit log, what happens is the data will be saved into our memory cache. So suppose a certain write request comes here, like there is a write request. So on this write request, what will happen is, as in a commit log, suppose I have this user 123, and there are some data, like suppose my name is there, SB. Okay, so I just put this thing into my commit log. Now memory cache or this mem table is an in-memory structure that stores or writes it temporarily. It typically implemented using something called a sorted map or a skip list. I'm not going again into the details of the data structure, but writes are added to the mem table as they arrive, and making reads and updates are very fast, because so you see this whole process that is happening. Okay, it is a it is just writing into the disk and then it is going into the mem table. So writing is super fast. So now you probably got the answer why we always say that in key value pair system, writing is super fast. So if you have to power the fastest writing system in the planet right now, probably like how RocksDB or any other kind of key value pair they powers themselves. This is the basic structure. Okay, so after this data, for example, in the commit log I am having this data. So after this, what happens is, in this stage the data is being written over here. So the memory cache is RAM, and of course RAM has a certain limit, and it is an expensive memory, right? So what we do is, once it reaches that certain threshold, based on the less frequent data, like flushing of less frequently accessed data, access data happens to the SS table. So for that, we again maintain some kind of a like a LRU cache sort of a thing, or LFU cache. So when is the least frequency of the data, and if the frequency is very low in a certain time span, then we keep on flashing those data to keep our memory free for the other incoming data. Okay. Now the structure of the SS table is also very important. So what SS table is stands for is, so after this we will go a little detail into the SS table. This is basically sorted string table. Okay. So sorted string table is nothing but it gives you the key value pairs, and as you can understand from the name, the key value pairs are being sorted properly. And also with this, there are a couple of things will come into play. That is, there is an index that is maintaining. The index will tell key in which portion or in the which memory location that particular key resides. Okay. And also there is something called Bloom filter, which we will discuss in detail what exactly a Bloom filter is. So Bloom filter, it is a probabilistic data structure that checks whether a key actually exists in SS table and give the data back to you in a very in a like a sub millisecond latency. When we will discuss in detail how Bloom filter is being designed, in this video only will do, it will be clear to you. Now why we are using SS table is, of course, optimized for the sequential IO, because that is the way it is being written, and which is way faster than the random IO. So whenever a random access memory we are trying to do, we need to go through all the records, and here we know from our index where exactly my data is residing. So it will be very easy and fast to get that data. And since SS tables are kind of immutable, they avoid the overhead of updating the data on the disk, and this is also perfect for the scalability that we have seen, the replication. So we think in this way, like the moment I have to do some kind of a syncing, whatever the data that is coming into my SS table, I can just sync as it is. Okay. And we are not changing any data, this all are appending, sorry, we are not doing any kind of update. That is why we call it immutable. We just keep on appending the data here, and whatever is the last updated data, we always access that. Okay. And this whole thing is also known as the log structure merge tree. That is again in way more detail. If we have to discuss, those things will come in play. So now probably we got the idea, but still just to uh, summarize, when a mem table reaches a threshold, we are going to flush our data to the SS table, and SS table is immutable and stored in disk, and great for syncing and the scalability purpose. So why not, you might be thinking that why I am not writing directly to the disk, why I am doing this commit log at the mem table. So probably you got the answer that why commit log is necessary. In case there is some issue in my server, that server powers off, how am I going to build my whole memory or my SS table? Suppose a certain log, a certain data comes here, and before writing into the SS table or the mem table, it vanishes. So I can actually build my mem table from the commit log, and some way that if even if the SS table gets corrupted, I can create my SS table from my commit log. That's why for this durability issues, commit log is a very necessary thing. Okay. And of course, like mem table, as you can understand, because we are putting it into a in memory, the data which are frequently used, it is very useful for them. Okay. So now let's explore the read path, how we are going to read. So Now again, the client or the user, he is going to make a read request. Okay, he is going to make a read request, and the read request will go to the server. Okay, and from server it will go to the, this is one of the important aspect where it should first go. As we were discussing, the initial read will happen from the mem table. Okay, if I am not getting anything into the mem table, probably at that point of time I will go into my SS table. So then the server will go to my mem table or my in memory cache. Okay, my in memory cache, it will look into, if there is a miss, if there is data, then definitely it will return from here only. If there exists any data, what it will do is it will just return from here if there are data. If there is no data, then what it will do is it will, from here, a new concept I'm going to introduce here is called Bloom filter. Okay, so it is going to look into the Bloom filter, and we will again go into the detail of the Bloom filter, how Bloom filter does all its magic. It will check into the Bloom filter, and Bloom filter in a probabilistic way will tell you whether a key, this is an important word, may exist. So there can be false positives as well. So Bloom filter will tell you that a key might exist or might not exist. For example, whenever we are doing things like our username, uh, we put username into Gmail. Okay, we put our, for new account we are putting username in Gmail. So Gmail then checks in a whisker of second that whether it exists or not. So what exactly powered that search in that single second? Does Gmail goes through all its account, do a select star from, or do a select count from this where username equal to this? No, it just uses Bloom filter, and Bloom filter gives you a with 100% rate that whether it might exist, and it can give you some false positive as well, but if it exists it will always give you yes. Okay, so again, how the internal data structure we will come in later. So from Bloom filter, if it say that your data might exist, what we will do is we will then go to the SS table, and from the SS table then we are again going to return our data. So if it returns, okay, the read request is going to return to the client. So this is on a very high level what happens to the read. So at first the in memory check happens in the memory cache. Its structure, in the memory cache structure, it stores all the data like the frequently served data, and it is typically implemented as a sorted map, and this gives us the fresh data or the frequently accessed data very fast. Okay, and then what happens is during SSTable lookup, it generally, before SSTable lookup, it generally checks whether in the Bloom filter the key might exist or not, and based on that, if it exists it returns. So one interesting thing I want to now touch upon is the immutability of SSTable. Okay, of SS table. So during immutability, what does it means? Like in SS table, whenever we are writing a data, suppose we are writing key 1, and with key 1 I am writing the value 1, and in some time another value of the key 1 comes, another value of the key 1 comes as v2. I am not going to delete the data. This is a very important thing. I am not going to delete the data. So rather, what am I going to do? I'm just going to keep on append. So that is why in SS table it only data gets appended and no data gets changed. That is why it is being called as immutability. And what powers this thing? So whenever a new data comes, okay, whenever a new data comes, we update our index as well. So suppose initially in the index it's been told that the key1 is in 0x EE in this memory. Now when the key1 is updated, it is in the 0x EE this memory. Okay, this is the latest one. This is the latest one. So what I am going to store in my index is this latest one, and this latest one will point me to the k1 of the v2 value. So this latest one will take me to this value, and this will basically help me to always get the last value. And how do we manage the old values? So we do some kind of a periodic cleanup if at all required, and this is also known as some methodology as merge and compaction. Suppose we have multiple SS tables, like a defined size. Suppose we have defined in our in our server, and we are getting multiple SS table in single server. So what we are going to have in that point of time is we will going to do something like a merge and compaction. So for different SS tables, we are going to merge all of them because there can be old and this kind of data which might not be our relevant one. And merge and compaction is a like a little bit of expensive process, so it generally happens in a time when our database load is a little less. So with merge and compaction, we keep the sanity of our SS table. And again, just remember, SS table is always and always it is immutable. Okay, now coming into how Bloom filter works, and after this we are going to conclude our this long video. So Bloom filter does its magic with nothing but a very long bit array. Okay, so what bit array is? Like, bit array will have this kind of things like, okay, now if I can just copy paste all of this thing together, something like this. Now suppose I am sending a user 123. Okay, suppose I am sending a user 123, and this user will be passed to a modulo hash function. So what this modulo hash function will give me is, this hash function will give me like some multiple bits. Okay, it will give me some multiple bits, and this bits will define whether this bit array like holds this particular user or not. So suppose my the data that it defines is 259. Okay, so what might happen is, this is 0 1 2, so this particular one I will mark as 1. 5 is 1 2 3 4 5, this will be my fifth one. 6 7 8 9, and this will be my 9, so I will set this thing as 1. So I am setting this 3 bits as true. Okay, now uh, suppose there is another user comes, so user 456, this key is coming. So again what I'm getting is 1 5 and 7 as my hash function bits. So 1 will be this, and 5 is already set, 6 7, so I'm going to mark this as bit. Now in position 5, probably you noticed there was already 1 was there, so it stays as 1. And again another item comes, suppose 789, okay, and it gives me 369, something like that. So 0 1 2 3, 3 is here, 4 5 6, and 9 is already being set. Okay, so now we see that we are having the overlapping bits as well. So now Bloom filter contains now these 3 users. So now case A, what I'm going to do is I'm going to search by search whether user 456 exists or not. So we are going to do hashes on top of it, the same hash function, the modulo hash function that I had, the same modulo hash function I'm going to use on this, and I'm going to have the 3 values on this, right? So it will give me 1 5 and 7. So I will check whether my 1 is set. I will see that yes. I will see whether 5 is being set or not. I will say that yes, and I will also check whether 7 is being set or not. I will say yes. So now bit 1 will tell, it is a probabilistic data structure, so the answer that it will give is probably exists. Okay, it will give me probably exist. Now why it is not 100% certainty it will exist, I will just come into in a, like, it might give you a false positive. I will just come into that example in a second. So before that, take case B. Suppose user 1000 is there, okay, and for user 1000 I have 0 2 and 7. So I see that, okay, the first one, the 0 itself is not set, so it is surely doesn't exist. Okay, so it is giving me probably exist and surely doesn't exist. And then there comes a case C. Case C is the false positive. Okay, so suppose there is a user, suppose some gibberish is there. Okay, now this gives me a similar hash 157. So I will see that 1 is there, 5 is there, and 7 is there. So what might happen is it will give you that it might or again exist, but in reality it doesn't exist. But in reality it doesn't exist. So when the way, this is the way the Bloom filter works, it is a bit array and all the bits are being set based on one of the modulo hash function that we are going to use. But you understand one thing, that this bit array, the larger the bit array that I am having, the more data probably I'll be able to accommodate, because my modulo hash function will be more liberal in that case. So this is how Bloom filter does the magic in this level. It tells you that, okay, the data is not existing for sure, so it will return not found, and the data might exist or might not exist. In that case, I will forward my request to a SS table. So this is what happens with the Bloom filter. And also there are some other nitty-gritty of it, but this video is getting will get very long. Probably all these things like the read path, write path, Bloom filter, log structured merge tree, SS table, they require their own videos, because those are hefty research papers which backed this kind of data structure, so it cannot be done in a single flow. But anyway, I tried to cover all the basic details, so it keep, like, you can keep on probing yourself by you can keep on probing by yourself on all the things. And just before concluding, the scaling, when we are talking about the scaling, it is never SQL versus NoSQL war. So in multiple database design discussions or in the forums, I have seen people are telling blindly that NoSQL doesn't scale. or sorry, the SQL doesn't scale and NoSQL scales very well, which is not really true. There are systems like financial system, like where the bank transactions are there. Suppose a global bank is processing millions of transactions daily, and they are doing it very easily with SQL. But of course, SQL, there will be a problem if there are petabytes of write in SQL. But in a system where we need banking transaction guarantees like the ACID guarantees and the complex join, in that case, we can easily scale our system with SQL. And when we are doing some kind of a thing like a real-time analytics or a lot of key value pairs we are going to store, where we do not need those hard-bound guarantees, and in that case we can use NoSQL or any family of the NoSQL. I think we just debunked one of the concept in our initial part also, like NoSQL is basically a family of databases. It is not really a single type of database. For example, SQL, when we say it is always RDBMS, in NoSQL there is no hard and fast thing like that. NoSQL can be anything. It can be the document DB, it can be a columnar storage, or it can be even a key value pair or graph databases. So that's the video, guys. Please do comment on please do provide your comment in the section if you have any doubt or concern. I will try my best to address them. See you in my next video, and as you are always is, stay awesome. Thank you very much.